Task 4 is all about sources. This is a simple point source. This is what it looks like. The particles are all born at these coordinates, 0, 0, 0 on the XYZ axis. Okay, and this part means the particles are isotropically evenly distributed and sent out in all directions evenly. But it's still a point source at 0, 0, 0. So this is our first more realistic fusion source, where we've taken that point source and we've taken an isotropic configuration and we've given it an energy of 14 MeV. 100% of the particles come out at 14 MeV. That's the energy distribution. And this is what the visual representation of the energy probability would look like. So not a bad start, but we can make it better. Here's an energy distribution for fission. This is the famous fission Watt spectrum. So the bins are a little bit noisy because I haven't simulated many particles, but in real life this would be smoother. But it's still a point source and it's still isotropic. So, to make the source more realistic, we should take into account the energy of the deuterium and the energy distribution of the tritium when they collide. They don't just collide with a single energy, each of them has a distribution due to the temperature distribution inside the plasma. They then form a helium-5 temporarily, and then it collapses and releases binding energy in kinetic energy of helium-4 and a neutron. So these two products have an energy distribution. Although they might have an average energy of 14.1 MeV, they have an energy distribution just as the input particles had an energy distribution. So this is a Muir distribution in OpenMC, and it's got an average energy of 14 MeV plus a little bit. The mass ratio is 5, that's for the input particles, and the temperature in electron volts is specified as well. It's still a point source and it's still isotropic, so I suspect we can do better still. The sources we've seen just there were perhaps suitable for modelling an ICF fusion device, but for a magnetic fusion device you want a spatial distribution as well, with particles at the edges being less likely than particles in the centre. So, we have made a parametric plasma source, and it takes into account plasma shaping parameters like elongation, major, minor radius, and triangularity. It also takes into account ion densities and ion temperatures. The result is that you get a plasma-shaped distribution, and the energy also has a Muir spectrum distribution. So again, I've not done many particles here, but if you did more, it would start to build up a plasma shape. The directions of this parametric plasma source are still isotropic, so they will go in all directions evenly. OpenMC can also do photon sources. So in this example, I'm modelling cobalt-60, which has two main energies at 50-50 chance, and the main difference between a photon source and a neutron source is you have to specify the particle as photon. So now I'm just going to run one of the tasks to show you how it works. Task 4, making particles, and I'm going to do the neutron tracks one, and I just want to show how to use Paraview at the end. So I'm just going to run the whole notebook and I'm going to look at the outputs. So now it's finished, I'm just going to right mouse click and I'm going to download the VTI, and I'm going to download the track files, and I'm just going to download 2 of these track files. Okay, and then I'm going to start Paraview, and I'm going to open. So now I've opened the VTI and the VTP track files, and I'm going to click Apply, and now we can see our tracks. To see the geometry, we need to select ID, and instead of outline, surface with edges, and that's our geometry, including the void geometry. So I'm just going to do a threshold, and I'm going to get rid of filter out the void. So there's our geometry, and I'm just going to make it slightly more transparent so we can see through it. Okay, now you can see the two particles going into two different materials. One of the particles scatters quite a lot before it's captured, and the other particle scatters very little before it's captured. Okay, hope you enjoyed task 4. Thanks very much for listening.